Hello everyone, thanks for coming to my presentation. My name is Torn Valdez and I'm going to be presenting my project using remote sensing to observe the long-term effects of high-intensity fire on riparian vegetation and stream hydrology. A little bit of background here. I'm also going to upload my slides just for reference because I have a little bit more information than I probably should have included. But past forest management practices have resulted in fuel loads that were higher than in a natural setting, which drive these large high-intensity forest fires, which we might call a megafire. This combined with the anticipated effects of climate change are anticipated to result in higher frequency of these megafires, which threaten people's lives and communities, of course, but they also affect critical wildlife habitats, water quality, and water storage capacity of watersheds by sealing surface soils and destroying plant communities in both large trees and the smaller herbaceous vegetation below, and as well as grasses, which leads to an increase in surface runoff, which goes into the nearest river system, increasing stream velocity, shear stress, and erosion. So the driving question that drove my study was, do high severity burns have long-term impacts on vegetation density that could impact stream hydrology that are detectable using satellite-based remote sensing? So I understood that going into this that more sophisticated processing and modeling techniques would be necessary to get quantitative conclusions using remote sensing, but I wanted to really see how the tools we received in this class, NDVI and false color imagery specifically, could be used to reasonably infer some of these changes to vegetation density and potentially to hydrologic function. So here's my study area. This is the Wolverine Fire, which was ignited on June 29th of 2015 on the northwestern bank of Lake Chelan. Lake Chelan is in the eastern slopes of the North Cascades in Washington, if anyone's unfamiliar with the area. I chose this fire because the high, moderate, and low severity burn areas were fairly similar in size in terms of acres. And this area has quite a few different water bodies which are listed here, mainly the Railroad Creek area, which runs through here and is the primary focus area, as well as Lake Chelan, which is this water body here to the east, and then the Entiat River begins here. These are the headwaters of the Entiat. So as a part of this, I downloaded 3 different data sets. The first data set was the Wolverine Fire data set from Monitoring Trends in Burn Severity, also called MTBS, that produced the images on the previous slide. And from USGS, Global Visualization Viewer, GLOVIS, I downloaded 2 data sets, one from June 23rd of 2015 and one from June 19th of 2019, and all of these are of the same area, which I reduced to make sure that is the exact same coordinates for each. And the GLOVIS data sets were captured by Landsat 8, so they had the same multispectral bands and the same capabilities and the same resolution. So I decided to do a normalized difference vegetation index for both the 2015 and the 2019 data sets, and then composite those by logically linking them to create the composite difference NDVI, showing the changes over the years, the bitemporal change detection. And then I also used the multispectral bands included in the data set to create a false color image to really further support the changes indicated by the NDVI. And I pretty much use that information to infer that in areas of high burn severity, if riparian vegetation didn't rebound and seemed to disappear as compared to the moderate and low or no burn areas, then then that is a good indicator that it lost some of its hydrologic function, resulting in increased erosion. So we'll begin with the pre and post-fire NDVI. The 2015 pre-fire NDVI is on top, and the post-fire 2019 NDVI is on the bottom. As you can see here, and this area circled in red, this is the north-facing valley slope of the Railroad River Valley. And this dark color in here, as you probably remember from our lessons on NDVI, the dark color represents a low vegetation density or poor vegetation health, while lighter shades of white and gray indicate higher density and or better health. So as you can see here in the 2019 image, you can't really see these white streaks that seem to indicate riparian areas based on the land cover and the aerial images I compared these two. Many of these areas have either disappeared or have really shrunk in size, especially compared to the south-facing portion of this valley, which can be fairly made out fairly well, and as seen in both the 2015 and 2019 image sets. So here's that composite difference in NDVI. The 2015 NDVI occupies the red and the blue channel, while the 2019 occupies the green channel. So the magenta colors on here represent higher reflectance by the 2015 NDVI, while the green colors, shades of green, indicate high reflectance by the 2019 NDVI. And as was supported in the previous image, the areas of high burn severity have this dark shading of magenta, and as you can see in these different areas as well. And all of these areas, from what I can tell using the MTBS data set and the images it contained, were high burn severity areas. And here's the full extent of the composite NDVI image. Down here is just like I thought a pretty cool area. This is an older fire that you can see is really regenerating its vegetation. Circled in red here is the Railroad River Valley, our focus area. And then here is like a reference area that we'll see in a few slides from now, which was an area of overall low burn or mostly no burn, really, to be compared with the primary focus area. So here is my multi-spectral image, my false color image, which I use the 754 band combination. That is shortwave, infrared 2, near infrared, and red visible light, respectively, and which occupy the red, green, and blue channels, respectively. And this, I've added some of the details here about each of those bands, but I thought this did a pretty good job of showing the extent of vegetation loss from 2015 to 2019 because of the fire. And I thought another interesting point was feature was that you can make out some of these riparian areas on this south-facing valley slope as it makes its way down to the Railroad River Valley. And true to the NDVI images previously, a lot of that has disappeared when you look at the north-facing valley slope. And like I said previously, here is the smaller subbasins to the north. Our focus area is circled down here in red for reference, but you can see that the areas of no burn, you can still account for pretty much all of those riparian areas and the intact communities at the lower valley bottoms here. So I thought that was a pretty good indicator that these high intensity fires not only affected the vegetation extent, but really seemed to somehow be affecting some of the riparian vegetation as well. And you can see here this little, what as far as I can tell, appears to be some sort of wetland in this little valley, in this higher mountain meadow. So as a result of comparing these different images, they weren't super clear in my presentation, but I could really see a loss in the high severity burn areas of some of the riparian vegetation communities, or the apparent riparian vegetation communities, from 2015 to 2019. Of course, some of this is due to the fire event itself, but in many of the areas you could see regeneration where there is low or moderate burn severity, but in the areas of high burn severity there really seemed to be a net loss of the riparian vegetation communities. And then as far as the limitations go, I thought in previous years any differences in precipitation or precipitation regimes could potentially affect the results that we see in these images, just due to any lack of water in previous years might affect the rate of regeneration by the vegetation. Also, NDVI has its own limitations in terms of being able to directly compare NDVI images. From what I've read, you're not supposed to do that directly because each NDVI is within the context of the reflectance measured by the sensors, and I've included the NDVI formula here just for reference in that regard. Any other environmental conditions that might have changed that are not necessarily related to the fire events that might not be documented could potentially impact the images that we have here. Oh, sorry about that. And then I also thought that the resolution of the Landsat 8, the sensors on Landsat 8, could be a potential limitation because you can't quite make out some of the finer details of these vegetation communities. So I included that as a limitation as well. So piggybacking off my last point, using high resolution imagery from other satellites or from UAV-borne sensors could potentially help to come up with more precise images that could be used to better infer and come to more quantitative solutions. I also thought incorporating more sophisticated analyses and methods, including a soil moisture indices such as normalized difference moisture index, could be helpful as well, which is beyond my skill set at this point. And then I thought that ground truthing and doing some on-the-ground surveys of the erosion and the vegetation loss in these areas would also be really helpful and really quantifying the extent of the effects of these high-intensity burns. But either way, I thought the results of this were pretty interesting, and seemed to support in some ways the loss of riparian communities after high-intensity fires, even years after the fact. So anyway, thank you for attending my presentation.